In this video, we'll talk about graphs of exponential functions. An exponential function is a function that can be written in the form f of x equals a times b to the x, where x is a real number, a is a non-zero real number, and b is a real number called the base of the exponential, such that b is positive but not equal to 1. When graphing functions, it is helpful to understand the graph of what we call the parent function. For exponential functions, the parent function is the exponential function with a equals 1, that is, f of x equals b to the x. There are two basic types of graph for the parent function, f of x equals b to the x, and the difference depends on the value of b. If b is bigger than 1, as you see in the graph on the left, then the graph has a horizontal asymptote at y equals 0, and as x moves further to the left, the graph is closer to the x-axis, but as x moves to the right, it grows very rapidly. This is, in fact, what we call exponential growth. On the other hand, if b is between 0 and 1, then you get what we call exponential decay. As x moves further to the left, the graph rises steadily, but as you're moving to the right, it decays. It goes to the x-axis, or it goes towards the x-axis asymptotically, and indeed, the line y equals 0 is a horizontal asymptote for both of these graphs. Let's talk about the graphs in a little more detail. First, let's talk about the case where b is greater than 1. This is the case where the function is increasing. The domain is all real numbers because b to the x is defined for every real number. The range is the set of all positive numbers. B to the x is always positive. So that means you don't get any negative values, and you don't get 0. B to the x is always positive. So the range is the set of all positive numbers. The y-intercept is the point 0, 1. That's because for all of these values of b, b to the 0 is equal to 1. Also, for all of these choices of b, the horizontal asymptote is y equals 0. That's because as x moves further to the left, the graph gets closer and closer to the x-axis. As we've already mentioned, b to the x is greater than 0 for all real numbers x. B to the x approaches infinity as x goes to infinity. As x moves to the right, b to the x grows without bound. And, as we've already mentioned, b to the x goes to 0 as x goes to negative infinity. For any choice of b, you'll have this same basic shape when b is bigger than 1. When b is less than 1, you have the mirror image of this picture. This is our second case. This should say case 2. This is our second case. b is between 0 and 1. In this case, you still have the domain as the set of all real numbers, and the range is still the set of all positive numbers. Indeed, the y-intercept is still 0, 1, because it's still true that b at 0 is equal to 1, and it's still true that b to the x is greater than 0. All we've done here is we've reflected through the y-axis, so much of what we had before is still true. The only thing that's changed is now b to the x goes to 0 as x goes to infinity, and b to the x goes to negative infinity as x goes to negative infinity. That's the only thing that's changed. These two have swapped. A shift to the right occurs when you subtract a positive number from the x value. So here we're going to assume that c is positive. So y equals b to the x minus c. So I'm subtracting c from the exponent. The graph of this is obtained by shifting the parent graph to the right by c units. So if you look at the graph that I have in gray is the parent function. This is y equals b to the x. And in order to obtain y equals b to the x minus c, we shift to the right by 3 units. As you can see, if we look at this y-intercept, we just pick it up and we shift it to the right by c units. So this length right here, that's c units. Notice that the horizontal asymptote does not change in this case. The horizontal asymptote is still y equals 0. When you shift to the right, you don't just shift the graph, you shift its asymptotes as well. So if we were to draw this graph, like so, we would want to shift that to the right, but also you also want to shift the horizontal asymptote with it. So let's just draw that in like so. So what I want to do is I want to just pick it all up and just drag it to the right. And you can see that the horizontal asymptote goes with it. But you can see the horizontal asymptote doesn't change because we're moving horizontally, not vertically. This is a horizontal line, so if you move it horizontally, it's the same horizontal line. What about the y-intercept? Well, the y-intercept is easy enough to compute. The y-intercept is when x is equal to 0. So that's y is equal to b to the 0 minus c, which is b to the negative c, which is 1 over b to the c. So the y-intercept is when x is equal to 0 and y is equal to 1 over b to the c, or b to the negative c, which is what it's labeled here. Notice that when you shift to the right, you obtain another exponential function. So y equals b to the x minus c. That's the same as b to the x times b to the negative c, which is b to the x divided by b to the c. So this is y equals 1 over b to the c times b to the x. So this is another exponential function. You see the same thing when you shift to the left. So again, let's assume that c is a positive number. Then you shift to the left when you add that positive number to x. So now we start with the parent graph y equals b to the x. And we want to graph y equals b to the x plus c. So you obtain this by shifting y equals b to the x to the left by c units. If you see a plus there, you're shifting to the left. So you can see that in terms of the y-intercept here. If I start with that y-intercept, I'm going to shift to the left by c units. So it's going to go like this, and this is c units. Again, it doesn't change the horizontal asymptote, so the horizontal asymptote is still the same. It's still y equals 0. What about the y-intercept? Well, again, that's just where x is equal to 0. So you have that y is equal to b to the 0 plus c, which is b to the c. So the y-intercept is 0 comma b to the c, which is what you see here. Now in this picture, b is bigger than 1. So when you raise it to the c power, you're getting something bigger. That's why it's higher up. But this is obtained just by shifting to the left. So if we draw the graph just very roughly, you can see that if we just shift it to the left by c units, you get the new graph, like so. Again, this is another exponential function. If you have y equals b to the x plus c, that's the same as y equals b to the x times b to the c. So you have y equals b to the c times b to the x. So again, it's another exponential function. Notice that the end behavior didn't change at all in either of these. If we look at the shift to the right, we have that the limit, well, we have that b to the x minus c still goes to infinity as x goes to infinity. And we have b to the x minus c goes to 0 as x goes to negative infinity. So it's the same end behavior. That doesn't change. And it's also true of shifting to the left. So b to the x plus c goes to infinity as x goes to infinity, and b to the x plus c goes to 0 as x goes to negative infinity. What about a shift up? So now let's call d some positive number. So a shift up is obtained by taking the y value and adding d to it. So that's what you can see here. Y is equal to b to the x plus d. So we start with the same parent function, which is right here, y equals b to the x. And all we do is we just take this vertex, or this y-intercept, and we just add d to it. And so it just moves up by d units. So this is d units. Now when you shift it up, you shift up the horizontal asymptote as well. So you'll notice that you now have a new horizontal asymptote, which is y equals d. So horizontal asymptote, y equals d. If we draw the graph, let's just sketch it roughly. So it's going to pass through that point, the y-intercept, and that point. So if we just roughly sketch this graph, like so, and let's draw in the y-intercept as well. Not the y-intercept, the x-axis, the horizontal asymptote. Now if we just shift all of this up, so let me just grab all of that. If we just shift it up by d units, you'll see that we end up with the new graph. And we also end up with the new horizontal asymptote, y equals d. So you can see that it's just a shift straight up. Now in this case, what is the y-intercept? The y-intercept is really easy to see in this case because you just take the previous y-intercept and add d to it. So we have a horizontal asymptote, y equals d, and our y-intercept, again, it's just when x is equal to 0, so y is equal to b to the 0 plus d, but b to the 0 is 1, so it's 1 plus d. So our y-intercept is 0, comma 1 plus d. The end behavior does change a little bit now, because now you can see that we have b to the x plus d. As x moves to the right, this still does go to infinity. However, now as you're going to the left, you're not going to 0 anymore. Now you're going to d. As x goes to negative infinity, as you move further and further to the left, we're looking at this graph right here. This is y equals b to the x plus d. You're looking at this graph right here. So as x is moving to the left, you're getting closer and closer to the horizontal asymptote, which is y equals d. So b to the x plus d approaches d as x goes to negative infinity. And that's simply because b to the x is going to 0. So you're just going to be left with that d. A shift down is essentially the same, but now you start with this positive number d, but now you're looking at b to the x minus d instead. So that means you're taking what was the y value and you're just subtracting d from it. But you can see it's the same basic idea. So we have these 3 points, and let me just draw a curve. We try to draw the curve through these 3 points, like so. And let's draw the horizontal asymptote, like this. And now we just want to shift everything down by d units. So you just shift everything down like that, and there you have it. So now, instead of having y equals b to the x, it's y equals b to the x minus d. So you can see that the y-intercept now is 1 minus d. The horizontal asymptote is y equals minus d, because we're moving everything down by d units. So you move the y-intercept down by d units, and you also move the horizontal asymptote down by d units. So that's d units. So now we have the horizontal asymptote is y equals negative d, and the y-intercept is now 0, comma 1 minus d. And the end behavior shifts as well. It shifts down. So as b to the x minus d, as x goes to the right, it still goes to infinity. So as x goes to infinity. But now, as x goes to negative infinity, b to the x minus d goes to negative d as x goes to negative infinity. And again, that's because b to the x is going to 0, so you're just left with this negative d. But in terms of the picture, you can see that it's as x goes to the left, you're getting closer and closer to this horizontal asymptote y equals d. We can also stretch our graphs. So suppose that a is a number bigger than 1. Then the graph y equals a times b to the x is obtained by multiplying all of the values of b to the x by a. So in particular, if you start with the parent function y equals b to the x, the y-intercept happens when y is equal to 1. So the new y-intercept, the y-intercept for y equals ab to the x, occurs when you take all of the values and multiply them by a. So in particular, if you look at the y-intercept, where the y value is 1, you multiply it by a, and you get a y-intercept of a. So in this case, we have the y-intercept is at 0, comma a. The horizontal asymptote does not change here. It's still y equals 0. And the end behavior is still the same. So a times b to the x goes to infinity as x goes to the right. And abx goes to 0 as x goes to negative infinity. So this should say as. So the end behavior doesn't change when you multiply it like this, when you scale it, when you stretch it. The same when you compress it. This is really another form of stretching, but now if we're still letting a be greater than 1, but now we're dividing by it. So y equals b to the x divided by a is just obtained by dividing b to the x by a. So here's our parent function, y equals b to the x. And in order to get to y equals b to the x over a, we simply divide everything by a. So in particular, the y-intercept, where y is equal to 1, we divide it by a to get 1 over a. So the y-intercept is the point 0, comma 1 over a. The horizontal asymptote is still y equals 0. The end behavior is still the same. So as you move to the right, you still go off to infinity. So b to the x divided by a still goes to infinity as x goes to infinity. And b to the x over a still goes to 0 as x goes to negative infinity. Now notice here we're dividing by a number which is greater than 1. So this is just a little comment here. So y equals b to the x over a. This is the same as 1 over a times b to the x. 1 over a is going to be some number between 0 and 1. Since a is greater than 1, it's a positive number greater than 1, 1 over a is going to be between 0 and 1. So this case where you're dividing by some number bigger than 1, so we're dividing by a, which is bigger than 1, this is the same as multiplying by some constant which is between 0 and 1. So that's why we didn't write that case down separately. Both of these cases, let me just go back one, both of these cases started with a being greater than 1. A greater than 1. That's because the case where a is between 0 and 1 is the same as this case multiplying by a between 0 and 1 is the same as dividing by a where a is greater than 1, because you can always take this division by a, so b to the x divided by a, and you can rewrite that as multiplying by 1 over a. So the case where you're dividing by an a greater than 1 is the same as multiplying by 1 over a, where 1 over a is between 0 and 1. So in other words, it's the same as multiplying by some number which is between 0 and 1. Let's look at an example. Use the graph of y equals 2 to the x to graph these two shifts. One is a shift up and one is a shift down. So first we're looking at y equals 2 to the x plus 3. So how are we going to go about doing this? Well, basically we start with this graph of y equals 2 to the x, which is what we have here. and we just want to shift it up by 3 units. So the best way to do that is to pick a couple of points. So we're going to start with this point, which is the y-intercept. Now that happens at y equals 1. So we're going to shift it up by 3 units. So 1 unit, 2 units, 3 units. So right here. So that should be our new y-intercept. We should also pick some other point. For example, what if we pick, say, 2 squared? So if we pick x equals 2, that's going to give us this point right here, which is 4. That's at y equals 4, is that point. So that's another point. So we can pick that one up and we can shift it up by 3 units. So we're starting at 4, 5, 6, 7. So we want to move it up to 7. So that means it's going to be right around here. You could also pick x equals 3, which is 8. That's going to move us off of the graph as it's drawn here, but that's going to put us at something like 9, 10, 11, something like right there. The other thing that we know is that we have a horizontal asymptote here of y equals 0, but we're going to shift it up by 3. So I can just lift this up and shift it up to 3 right here. So this is my new horizontal asymptote. So I have a curve with this horizontal asymptote that's going to pass through these points. So I'm not going to be able to draw a perfectly drawn curve. This is just going to give us some general idea what it looks like. So it's going to just go through these points. It's going to go up like that. And it's going to have this y equals 3 as a horizontal asymptote. So it's going to look, let's draw it like this. So it's going to look something like that. So this is our new graph, y equals 2 to the x plus 3. What about our second graph? This is the same basic idea, but now we want to shift down by 3. So we do it the same sort of way. We just pick some points. So we pick the y-intercept, and that's at 1. And we want to move it down by 3. So 1, 2, 3. So that's going to put it right here. We're also going to take this y-intercept, or not this y-intercept, but the horizontal asymptote. So the horizontal asymptote is y equals 0, and we're going to shift it down 3 units. So that'll be down right there. So this is y equals negative 3. So that's our horizontal asymptote. And now we can just take these other points like we did before. So here's the point 2, 4, and we want to shift it down by 3 units. So that's going to take it down to 1 right there. And we can now take this x equals 3, 1. Oops, that's steered off a little bit. That's going to correspond to this point right here, which is, of course, 3, 8. And this one's 2, 4. Again, we're going to shift it down by 3 units. So if it's at 8, that means it's going to be at 5, which is right here. So it's going to be roughly right there. So we want to connect these dots like so. And we're going to have a horizontal asymptote of y equals negative 3. And this is our sketch. Y equals 2 to the x minus 3. Now with technology, I could actually just do it a little bit more easily because I could just trace this out like so. Something like that. And then I could just pick it up and I could just move it down like so. And you can see I did a pretty good job. Anyway. In this example, we want to shift to the left and right rather than up or down. So now we're looking at y equals, our parent graph is still the same, it's y equals 2 to the x, like so. But now we're going to shift to the right by 1 unit. So remember, that's when you subtract 1 from the x, that means you shift to the right by 1 unit. So I'm just going to take this whole picture here and I'm just going to shift it to the right by 1 unit. So our y-intercept is going to shift to 1 unit to the right, so it's going to go right here. That's not going to change our horizontal asymptote, by the way. If you shift a horizontal line to the right, it's still the same horizontal line. What about this point here, 2 to the 4? Excuse me, 2 comma 4. 2 squared is 4. So we're going to shift this one to the right as well. So that's just going to go right over here. And we can just shift one other point. So I would shift this one, but yeah, I guess we can do that. It's going to go to right about here. And so that gives us our graph. Now the horizontal asymptote is still the same. So it's still not going to cross this y-axis, or this x-axis rather. So we're going to connect the points something like this. There we go. And this is y equals 2 to the x minus 1. Notice this y-intercept here. We actually can figure out what that is. Y equals 2 to the x minus 1. Of course, if you plug in x equals 0, that's just going to give you 2 to the negative 1. So this y-intercept right here, this is happening at when x is equal to 0 and y is equal to 1/2. Now notice that y equals 2 to the x minus 1. We can rewrite this. Y equals 2 to the x times 2 to the negative 1. So this is really y equals 1/2 times 2 to the x. So really what we're doing is we're dividing all of the y values by 2. So our y-intercept is at 1, but we divide it by 2 to get to 1/2. What about this point right here? This point where x is equal to 2 and y is equal to 4, we divide it by 2 and we end up with 2. So as you can see, this point right here, if I could draw a straight line, you could see that this point right there would be at 2 comma 2. And what about when x is equal to 3? So in that case, we have y is equal to 8. But again, you just divide all the y values by 2, and what do you end up with? You end up with 4. Right there. So you can see we're just dividing all of the y values by 2. What about this one? Y equals 2 to the x plus 2. Well, here we have a plus, so that means we're going to shift it to the left. We're going to shift it to the left by 2 units. So let's do that. So we start with the y-intercept, and we're going to shift it to the left by 2 units. So that means it's going to be over here. Now let's pick another point. Let's just make it easier and just on ourselves, and we'll just pick when x is equal to 3, and of course we know that that's 8. But we're going to shift this 2 units to the left as well. So that's going to put it over here at 1, like so. So this is, we're shifting everything to the left by 2 units. And what about the y-intercept here? Well, we know that so in order to get the y-intercept, that's when x is equal to 0. So that's going to give us y is equal to 2 to the 0 plus 2. 2 squared is 4. So that's right here. So that means we're just going to connect these points like so, and we're still going to have the same horizontal asymptote. So this is our graph, y equals 2 to the x plus 2. Now in this case, we're looking at 2 to the x plus 2. That's 2 to the x times 2 squared, which is 4 times 2 to the x. So really what we're looking at is we're taking the parent function and multiplying everything by 4. So indeed, if you look at the y-intercept, which is 1, you multiply it by 4 to get the new y-intercept, which is 4. And for example, what about here? When x is equal to 1, that gives you a value of 2. So this point right here is 1 comma 2. And so we're going to take that x value, 1, and that's going to give us a y value of 2, and we're going to multiply that y value by 4. So that's going to put us all the way up to 8, which is right here. So really, when we're shifting to the left by 2, what we're really doing in this case is we're multiplying everything by 4. That's just in this case, because our base was 2 and we're shifting by 2, and 2 to the 2 is 4. So that's where this 4 comes from, 2 squared. When we're graphing, we might also want to do a reflection. So in particular, the graph y equals b to the minus x is obtained by reflecting y equals b to the x through the y-axis. So in terms of our graphs here, we have the parent graph y equals b to the x. And if you replace x with a negative x, basically that means you're just moving in the opposite direction. So instead of increasing as we go to the right, we'd increase as we go to the left. So this is y equals b to the negative x. So changing x to negative x is like reflecting through the y-axis. Now notice that y equals b to the negative x is the same thing as 1 over b to the x, which is the same thing as the quantity 1 over b raised to the x. So this is still an exponential function. B to the negative x is still an exponential. It's just now it's 1 over b raised to the x. And you can see that it has that exponential decay instead of the exponential growth. On the other hand, if you put the minus sign in front of the b, then you end up with y equals minus b to the x. And in this case, you're reflecting through the x-axis. Y equals b to the x is always positive, so if you put a negative in front of that, you get something which is always negative. In this example, we'll use the graph of y equals 3 to the x, which is given here, to graph y equals negative 1/3 times 3 to the x. So this graph that's given is the parent graph, y equals 3 to the x. So what we're asked to do is we're asked to now graph y equals negative 1/3 times 3 to the x. So the first thing that we want to do is we're going to multiply by 1/3, and then we're going to put a minus sign in front of everything, which will be a reflection through the x-axis. So we'll first do the multiplication by 1/3, and then we'll do the reflection. So if you're multiplying by 1/3, that means you divide all the values by 3. So in particular, if you start with this y-intercept, which is when y is equal to 1, that's going to become 1/3, which is about here. Let's pick some other values. So for example, if we pick the x equals 1, that gives us y equals 3. So this is the point 1, 3. And so we want to divide this by 3 as well. So that's going to take us to 1. So it's going to be right there. We can't go so far as to 2 on this graph that we see, because 3 squared is 9. That would be up here somewhere. But we want to divide that by 3. So that's going to just give us a 3. So that's going to give us here. That's this one. We might not be able to see x equals 2, the case where x equals 2 on this given graph, but that's the case where x is equal to 2 in the parent graph, so y is equal to 9. So that's up here somewhere. But we're going to divide that by 3, so 9 divided by 3 is 3, so we're down here. So if we were to connect these points, let's just do this quickly. Let's just draw a little curve through these. This one is y equals 1/3 times 3 to the x. Actually, this is 3 to the x minus 1. So you could also view this as shifting to the right by 1. And you can see that here. We shift to the right by 1. So you could also view it that way. But that gives us y equals 1/3 times 3 to the x. But what we actually want is minus 1/3 times 3 to the x. So I need to put a minus sign in front of this, but that just means reflecting everything through the x-axis. So instead of having this graph, we're going to have the same thing but down here. So let's just reflect all of these points, for example. First we reflect the y-intercept, which gives us this point. Next we'll reflect this point where x is equal to 1 and y is equal to 1. So 1 is right about here. So that'll give us this point. And now we want to reflect this point where x is equal to 2 and y is equal to 3. So 3 is going to go to negative 3, and that's going to put us right about here. So this gives us some points. Usually having about 3 points is what you need in order to graph these things. Now we have the same horizontal asymptote, it's just we're reflecting through the x-axis, so the horizontal asymptote's not going to change. So it's going to look like this, like so. So this is y equals minus 1/3 times 3 to the x. Let's just comment that the horizontal asymptote here is still y equals 0, and the y-intercept is now the point where x is equal to 0 and y is not positive 1/3 but minus 1/3. So that's the graph of y equals negative 1/3 times 3 to the x. Here's another example. Use the graph of y equals 3 to the x again, so this is still the same parent graph. Y equals 3 to the x. But now what we're graphing is y equals negative 2 times 3 to the x minus 2. So notice that we have the parent graph 3 to the x. What we're going to do with this is we're first going to multiply it by 2. That's the first step. Then you reflect it. And then the last step is to translate down by 2. When you subtract by 2, that's translating down. But the first thing we're going to do is we're going to multiply by 2, and then we're going to reflect it. So how's that going to work? So let's multiply by 2. So let's just pick a few key points here. So we want to multiply this by 2, so it's going to, so the y-intercept was 1, but it'll now be 2, like that. And let's see, what about when x is equal to 1? When x is equal to 1, this gives us the point 1, 3. We want to multiply that by 2, so that's going to give us 6. Maybe that's a little too high. 6, like so. So this is going to give us the point 1, 6 on this graph. So first thing I'm doing is I'm multiplying by 2. So let's just connect these up a little bit. So this is going to be something like this. So the next thing I want to do is reflect it. So let's change the color. Let's change the color and we'll reflect it. So now all of these points just go down here. So 2 goes to negative 2. So it'll go to negative 2. And 6 goes to negative 6. So that's going to be down here, like so. And now we connect it. We're just doing a rough sketch here. Now the last thing that we want to do is we want to translate everything down by 2. So now we just shift everything down. Now this is actually going to leave the screen pretty quickly, but we're going to shift this one down by 2, so it'll be here. Now the horizontal axis, which is our asymptote, that's also going to get shifted down. So this is our horizontal asymptote, and it's going to get shifted down by 2, so it's going to get shifted down here, like that. So it gets shifted down by 2 units. This point right here also gets shifted down by 2 units, but that's not going to fit on our screen, so it's going to look something like this. Something like that. So this is going to be y equals negative 2 times 3 to the x minus 2. Now in this case, our horizontal asymptote is now y equals negative 2 because it got shifted down. And what about our y-intercept? Our y-intercept is right there, it's negative 4. So it's 0, x is equal to 0, and y is negative 4. And you can see that if you just plug it into here. So the y-intercept, that's when x is equal to 0. Negative 2 times 3 to the 0 minus 2, 3 to the 0 is 1. So that's just 1. So you have minus 2 is negative 4. So that's a good way to check and make sure that you've done it right. For this one, we're just asked to describe the end behavior of the graph. Now, in order to do that, it helps a lot to know what the graph looks like. So we'll probably want to sketch a quick graph, but we won't be quite as precise as we were before. So in this case, the parent function is y equals 5 to the x. So if we were to just roughly sketch what that graph looks like, it looks something like that, y equals 5 to the x. The next thing you do is you multiply it by 4, which is going to just increase everything a little bit. So it's going to be more like this. And then we reflect it. So we take this curve and we reflect it. So it's going to be something like this, or maybe a little bit bigger, so something like that. Y equals minus 4 times 5 to the x. But now what we want to do is we want to translate everything down by 10. So basically you want to pick this curve up and move it down. Now it had this one, y equals minus 4 times 5 to the x. This has a horizontal asymptote at y equals 0. So you just want to move that down. Let's change the color. So we're going to move everything down by 10 units. So the horizontal asymptote goes down by 10, which is going to be down here somewhere. So this is going to be y equals negative 10. And then we're going to have our graph that looks kind of like that. So this is y equals negative 4 times 5 to the x minus 10. Now this is not a precise graph at all, but we're just trying to determine what the end behavior is. And we can see that now from looking at, let me just get this straight. Okay, so we can see that now just from looking at the graph. You can see as x goes to infinity, this thing is going to drop. It's going to decrease without bound. So y is going to go to negative infinity as x goes to infinity. And if as x goes to negative infinity, you're going to be over here, and you're going to go to the horizontal asymptote, which is y equals negative 10. So y is going to go to negative 10 as x goes to negative infinity. And that's the end behavior. Really, you don't need to look at the graph to see that. Let's take a look at what we see here. Now, as x is going to infinity, 5 to the x is going to infinity. And if you multiply that by a negative number, negative 4 times 5 to the x is going to go to negative infinity. And if you subtract 10 from that, that's not going to change anything. On the other hand, as x goes to 0, not 0, as x goes to negative infinity, this term is going to go to 0. And if you multiply something which is going to 0 by negative 4, that'll go to 0 as well. So you'll just be left with a negative 10. It sort of helps to look at the graph just so you know what's going on, but it's not absolutely necessary. What about this one? Describe the end behavior of this graph. Okay, well let's do the same thing. Let's sketch the graph briefly. We don't need to be accurate at all. We're just trying to figure out what the end behavior looks like. So the first thing to do is to graph the parent function. Now, the parent function in this case is y equals 2 to the x, which is something like this. Now this is 2 to the negative x, so that means we need to reflect it. So it's going to end up being like that. Well, let me just try a little bit harder, like that. So this one is y equals 2 to the negative x. And now we want to multiply that by 2, so it's going to get bigger. And then we're going to translate it upwards, so maybe we need a little bit more room. So let's put this down here. So the next thing we're going to do, so this is y equals 2 to the negative x. Now we're going to multiply it by 2, so everything just gets bigger. So it's going to look like that. So this is y equals 2 times 2 to the negative x. But now we just add 4. We're going to add 4 to it. So we're going to take all of this and we're going to move it up by 4 units. So that's going to take the x-axis and it's going to move it up by 4 units. So everything's going to be moved up by 4. Just for fun, let me just determine what the y-intercept is here. So this is when x is equal to 0, so this is going to be 2 right here. So that's 2. This is 1. So we're going to move everything up by 4. So this y-axis, which is or this x-axis, when y is equal to 0, that moves up to 4. So that's going to be up. So if this is 3, 4 is going to be right up here. Let's just change it to blue, just to draw this. So that's going to put us right here. So that's where this is y equals 4. So this is our horizontal axis, y equals 4. So I'm going to just take this picture, this graph, and I'm going to shift it up by 4 units. So it's just going to look something like that. So this is y equals 2 times 2 to the negative x plus 4. And again, this isn't an accurate graph. I'm just trying to get an idea of the end behavior. And now I can see that y goes to 4 as x goes to infinity, because as x moves to the right, you're getting close to the horizontal asymptote of 4. And as x goes to the left, you can see we're increasing without bounds. So y goes to infinity as x goes to negative infinity. Once again, you could just look at this. You don't really need to look at the graph. As x moves further to the right, and x becomes increasingly large, this is 2 to the negative. So this term right here, that's 1 over 2 to the x. So as x gets larger and larger, this 1 over 2 to the x is becoming smaller and smaller. It's going to 0. So as x moves to the right, this term goes to 0. Multiply it by 2, it still goes to 0, and you add 4. So that's why as x goes to the right, you end up with 4. On the other hand, as x goes to negative infinity, 2 to the negative x, well, negative x, if x is already negative, then this minus sign x, negative x, is a positive number. So it's 2 to something large, some positive number. So this thing becomes huge. So if you multiply it by 2, it becomes even larger. And then if you add 4, it becomes larger still. So it's going off to infinity. What about this example? Y equals 2 times 1/2 to the x plus 3. Well, this example is not much different than the last example, because in fact, this is 2 times 1 over 2 to the x plus 3, which is 2 times 2 to the negative x plus 3. So this example is almost exactly the same as the last. So the last example is 2 times 2 to the negative x plus 4. And now we're just doing plus 3. So we're going to end up with exactly the same thing, except now our horizontal asymptote is going to be y equals 3. So that tells us that we're going to have the same basic shape, but it's just going to be down 1. So the graph here, the graph in this case, is going to have horizontal asymptote at y equals 3, which is, let's say, right here. But otherwise, the shape is going to be basically the same. It's like that. So we're going to have that y goes to 3 as x goes to infinity, and y goes to infinity as x goes to negative infinity.